Okay, let's start. So, firstly, uh, regarding this thing, so firstly, Amr is back. So, grading is started, I guess. Is back hale and hearty. This Friday, um, G, who's kind of the informal TA, he's going to make a presentation on how to go through the schematics and make sense out of it because questions from Trevor, and I guess were you the anonymous person who asked the heart rate question? No, who was there someone who asked? Okay, there were two heart rate questions, and I guess in both of them, kind of a bit of reading the schematics and all was helpful. So anyway, so Friday's discussion section will be devoted to that. Um, uh, Today, what I'm going to be doing is firstly kind of continuing on that ML theme, but I also wanted to walk you through how to go around analyzing a real data set in Python. Just some of you have possibly seen it if you have done an ML course, but would be useful. There's a wealth of material out there on the web, and so basically I've kind of borrowed some stuff from that to kind of walk you through that. But prior to that, I want to kind of go over some of the other classifiers um, that exist. So last time around, we kind of looked at uh, pre-processing of sensor data. And if you recall, we talked about there are problems such as missing data, noisy data, etc. And some of this cleaning up, like noise and all, you might want to do it even in the hardware side. So of course, in this course, you're given the hardware that is. Missing data can happen, particularly if you're doing your inferencing and all, let's say on the Raspberry Pi side or perhaps even a cloud service potentially. Um, so that sort of obviously ends up creating issues because of networking software, those kind of issues. So it's not that the sensor has to necessarily not be sensing. Hardware tends to be fairly reliable generally. So data loss usually happens kind of subsequently, and then you have to kind of fill it and somehow be graceful in coping with it. Occasionally, it could even be because the sensor is bad, like maybe the wiring or something like that. Okay, so that was one. Another pre-processing was too much data, and it's sensor plus sensor dependent. And our answer to all of that was to have features. So instead of using the raw samples as they are, we take windows of some time that you pick based upon your uh, domain knowledge of the application, something over which you don't expect things to change widely, and yet not. So you don't want like the window during which lots of different activities may happen. So usually the features over a window and the window sizes are uh, tens of millisecond to seconds, depending upon the application that that you would have if you are doing some sort of a sensing in, let's say, occupancy in a home. You're trying to detect that. Perhaps seconds would suffice. On the other hand, if you're doing something like an activity using um, the accelerometer sensing, then you're probably in tens of millisecond regime. So a lot of it just kind of comes from intuition. We talked about how there are temporal features, and you have spectral features, and then there are features about the contextual features, if you may, right? Like um, the, associated with the whole sequence. So temporal features were things like what's the average, median, variance, those kind of things. Spectral, which frequency component, where is the centroid of the spectrum, and contextual are like time of day or those kind of things. So there are a whole bunch of these features that potentially kind of are there. The second thing we started on was the ML algorithms themselves. And there is a whole bunch of them, but even before that, we kind of had a broad categorization: supervised versus unsupervised. versus a whole bunch of others, which we are not bothering with. But supervised basically says that, look, you are going to have some data set which is appropriately labeled, that is, you know the answer, and then using this representative sample of input and answer, you learn the parameters of a model, and once you have trained that model, then you apply it so that given an unknown x, you can now predict the y. So much of usage of machine learning happens in this supervised regime, and really different things differ upon what mathematical model you are using. Is it a linear function? Is it a neural network? Is it some sort of a decision tree or things like that? So we started with naive Bayes last time, and we're going to look at a couple of more today. Um, uh, Now, a challenge with supervised, which those of you who are doing projects of that nature are probably hopefully realizing that collecting the data and actually more importantly labeling it is pretty painful. In fact, labeling is uh, called as the blue collar job of AI. And getting high quality labeled data is often extremely hard, extremely intrusive. So, so then the thing is, you approach the problem as, can I design a system where either the labels don't need to be provided, or the burden is a lot less. So there are lots of methods, lots of research doing addressing those kind of things. There are notions like unsupervised learning, which we see, and the idea out here is that just given the x, the inputs, we will cluster them in some manner because they appear like some inputs obviously go together, other go together, so you kind of cluster them, and then you approach the human or the expert to label the clusters. So instead of labeling each individual data point, you are labeling entire cluster, so you're minimizing that effort. Another one is that perhaps an initial labeling could be done through some sort of expert rules that may be given. So you may have some sort of a rule which may kind of go ahead and label the data, and much of what needs to be done could be done through that, and then only you apply some correction on top of it. So an initial proposed labeling could be done by that. You can also simplify these things via uh, having a more intrusive sensor just for the training duration, so like a camera. So like you can ask the person, let's say you're trying to get the labels for activities, then perhaps for that duration you can ask your cohort of uh, uh, people who are part of your training data collectors. They can perhaps wear some sort of a camera, and you collect that information, or put additional stuff like maybe they can carry some sort of a device with which they can voice annotate, say I started walking, started, right, something. So you can approach it as a human computer interface type problem. In some work I have seen that at the end of the day they will portray to you kind of your sensor data trace with a first guess of what activity you were doing labeled on it, and then you can just go and correct, a little bit like your email client say, I think this is a spam email, and then you can say not a spam. Okay, so you can kind of correct that. So there are a variety of ways you can approach it, but it's a super important problem, and in fact in many domains that's really the challenge, lack of large quantities of this kind of data that you kind of need. There are other learning paradigms which again are based around this notion that could we move away from this. The other, I guess, in recent years has been the emergence of deep learning, neural networks, and these things kind of at some level on the same realm. It's just that they need a lot more data and a lot more computation, and therefore um, qualitatively also, but more importantly in terms of the tools you use, they rely kind of on a different thing. So much of the other machine learning, you'll just use things running on your regular computer, regular CPU, but deep learning pretty much forces you to get to GPUs or accelerators of those form, because if you don't, you're looking at training times of hours versus weeks or months, okay, and kind of that huge difference just makes things very different. Okay, we also saw, um, I guess I'm going to carve out here, the first knife-based classifier as the very first one. And the challenge out here is the following, that while there are excellent tools for machine learning, there are Python-based tools, there are Java-based machine learning toolkits. R is a programming language catering to this. Unfortunately, they all are optimized for data scientists who are kind of interactively working with these things. When you are looking for something which you can now export and deploy, things exist for server type machines, but really there is nothing which says spit out a piece of code which I'm going to run on Cortex M processor core. Okay, it just isn't there. So the challenge that when we are in the embedded space phase, someday this will change, and there is active research that is kind of seeking to do that. But right now, this does constrain your choices. Okay, that is, either you kind of implement your model from scratch, or it's a lot of effort. So the other alternative is to keep things to simpler models potentially. So knife-based classifier falls into that category because its implementation, once you have the parameters, is super simple. Unlike some of the others that we will see, where even the inference phase requires at least a complicated logic flow for your program. Okay, even though computationally it may not be terribly hard. Okay, so that's by way of recap. What I want to do is to go over some additional details about knife-based classifier. So if you recall, the basic idea in knife-based was the following: that our goal is, given observation X, we want to find the label Y. So given the feature vector for a particular window X, we want to find the label Y, and the feature vector has a whole bunch of features in them. So we call them 1 through D, and basically we are given what we are interested in is a joint distribution of X given Y, because that is what appears top right. This particular term, but calculating that from the kind of data that you would have in the presence of large D is going to be pretty hard. Just not enough data. It's called curse of dimensionality. So essentially, the assumption that we make is that conditioned upon Y, that is, if I know what label it is, what activity it is, then X are independent. The various attributes are independent. This is certainly not true in real life, but let's say were it to be true, then I can write it as a product like this, and now all I have to do is to estimate for each one of those attributes independently, and that I could seek to do much more easily. So while it is possible that let's say each xi can take 10 values each, then it's 10 to the power d. Maybe not all those combinations will exist, but if I'm only looking for each one of the 10 values of x1, they may still occur. So this breaking it like this helps tremendously, and then our problem basically becomes find that y which maximizes py given x, which translates into maximizing this particular term out here. So there are parameters corresponding to this. These are our parameters now, right? So these two probabilities are our parameters of a model, and we need to kind of learn those. So the way we learn these things, in case of categorical variables, that is, attributes which take values out of a set, uh, um, whatever type of fruit, or was there motion or no motion, or stuff like that, I can basically do counting from my data set and calculate it, but we kind of run into a little snafu, which is, if some value never occurs in the data set, if a particular px given y doesn't occur, then that term in the numerator is going to be 0, and since we have a product sitting out there, everything becomes 0. So to cope with that, we do a little bit of a smoothing, and we basically add a smoothing factor L, and in the denominator it will appear as L times M, where M is the number of distinct feature vectors that can exist. So we do a little bit of smoothing and end up with these formulas. In essence, what this is saying is that we started out with some assumption about the values of these parameters. And this relates to, in statistics and probability theory, what's called as Dirichlet distribution. So kind of the idea is the following. Let's say I have a coin. You would have a prior on that heads and tails are both half. But let's say I toss it, you get a head. I toss it again get a head. Toss it again. Each one of these are providing you some evidence about the nature of the coin, because the coin could be potentially biased. So I started out with kind of a uniform distribution, but each observation is kind of leading me to kind of some sort of a distribution where if I see first 100 heads in a row, I may say maybe there's something wrong with this thing. So I would begin to have a peak around head and kind of move away. So the probability p with which the coin gets the head or the tail, that I'm trying to estimate its distribution. So I start out with kind of saying my prior is I solve uniform, and that's basically what's happening out here. So this is called Dirichlet distribution, and we encounter it a lot, right? I mean, we have a prior on some topic. In the coin case, I had a prior that the probability of head is 0.5, but then as I see more observations, my estimate of p begins to change. Likewise, here for the parameters, we will say the prior is going to be something which basically the L basically says the prior is everything is equal.
So is there anything for the above explanation you gave for non-negative matrix factorization to be applied for name base? Because we don't generally apply PCA.
No, so I don't understand your question.
Some models don't take the negative values.
Well, there are no negative values here.
No, I mean, when we feed it into the model as such,
Uh-huh.
we apply NNMF instead of PCA. Because PCA can contain negative values.
No, but what does it have to do with this?
No, I mean, what is the reason for, like, why can't PCA be applied for dimensionality reduction?
Yeah, those are two entirely separate issues out here, right? I mean, what the dimensionality reduction that you're referring to in case of the PCA is how I would decide perhaps on the features I have or stuff like that. Here, all it is saying is once I have a feature vector, I may not have enough data for it to estimate each occurrence. So just again, take an example, right? I mean, if I have 10 feature values and each one of them can take certain set of values, let's say each one of them can take 5 values, okay? Then I have, and since I have 10 features, 10 attributes, so I have a total of 5 options times to the power 10, 5 to the power 10. I will be required to see all those 5 to the power 10 occurring sufficient number of times in my training set, and that's already huge, okay? So by separating it out, we're basically saying each dimension, I need to have an observation for every value. And even then, I may not have it. It's possible that some particular attribute or some particular dimension is very rare, and that will lead to a 0 up there in the numerator, and that's going to cause us problems. Okay, so this is what we end up with um, in case I have categorical values. But what if I have continuous values? But so we'll see the answer to that a bit. But before that, this is just an example. So this is again that running data set we had of accelerometers, or whatever, inertial sensors on the person and other sensors on the out there. So from that Washington State data set, what we have is the following. These little x's, x1 through x7, represent 7 windows of observations, and the rows represent the different features, different attributes in the feature vector. So it includes day of the week, time of the day, hours, bathroom sensor count, medical cabinet sensor count, energy in the hip accelerometer z-axis, and activity level. Okay, well, so 5 features, and the bottom row is the ground truth. Okay, that's the label we have. So in this case, we can see that the probability that x1, which is the day of the week, takes the value 1, given that the activity is personal hygiene, which is y equal to 1, it was elsewhere. Then p x1 equal to 1 given y equal to 1. So we can say that y equal to 1 occurs 3 times, and within that x give, sorry, within that day of the week takes the value 1 only once, so the answer is 1/3. So I kind of do this kind of frequency counting. Similarly, you can see that probability x1 equal to 1, y equal to 3 is also 1/3 3, and I can also count probability of y equal to 1 and y equal to 3. So I can do this kind of frequency counting and uh, in a pass through the data. Now, how do I handle continuous features? Some of the features here were continuous. Actually, one of the feature. So if you look at out here, this is a continuous feature, right? Uh, Real valued. So now, potentially I can take these real valued thing and think of them also as coming categorical in the sense that they are coming from a very large set of values, but that's usually um, not not a very useful view to that's not a very useful view to take. What can we do for it? So a very common the way you handle this thing is the following. We basically say that any given distribution like that, so probability of xi given y equal to j, we are going to say that it's Gaussian distributed. So it has two parameters now, the mean and the standard deviation, and those could be, the mean is going to be the expected value of xi given y equal to j, and standard deviation or rather variance is going to be given by the usual formula out here. And this we can estimate. So essentially, we estimate these using the samples that we get. So now we have these parameters, and we can use these to figure out our probabilities. So in this particular case, considering this energy, you can calculate that the mean that for x5, given that the activity level was 1. So basically, these are three such instances, so 500, 506, and 521. I calculate the mean, I calculate the variance, and likewise, I calculate it for the case where activity level was 3. So now I have these distribution parameters for the two activity levels. And now we can answer a question like, let's say I'm given a feature vector which happens to have x1 equal to 1 and x5 equal to 250. So let's say we were only sticking with feature vectors of two attributes. So now what I can do is I can calculate what the probability of y equal to 1 is given those observations, and likewise what's the probability of y equal to 3 is given those observations. So probability of y equal to 1 given x1 equal to 1 and x5 equal to 250 is, because of our assumption, probability of x1 equal to 1 given y equal to 1 multiplied by probability of x5 equal to 250 y equal to 1 multiplied by probability of y equal to 1. Each one of those parameters we had estimated from the training data. You kind of multiply these things together and you get some insanely small number, 10 to the power minus 189 out here. Okay. We do the same game with probability y equal to 3. Again, multiply it. Again, I get a number which again small but is bigger, and therefore in this particular case the answer is going to be y equal to 3 because that activity has a larger probability. So that's how naive Bayes works. As you can see that once you have the model parameters, it is super simple to implement. So it's a probabilistic approach to classification, and its really key point is super simple. And also, I guess it gives you a probabilistic feel to the whole system, so which has its own advantages. But it does require that you know those probabilities and you can learn them from training set, or you could also have some cases come from domain knowledge. Maybe the underlying physics works that way. Maybe you know it is uniform, things like that. Surprising thing is that even in cases where the independence doesn't hold, the conditional independence, NBC still gives terrific results. And so you would often find that it is actually better than kind of the more complicated classifiers that you end up using. So that's what naive Bayes is. Now, uh, uh, of course, there are many situations that it doesn't work with. So let's see how can we extend this thing to more general case of continuous things. So we saw a little bit. We said attribute continuous attributes, we can think of them as Gaussians. So that gives, in addition to sort of what I showed, how you could use them in practice, it also gives some nice theoretical properties, and so you can kind of do some further analysis and all. But the question is that is it sufficient? So let's take this case, okay? So let's say we are looking at eating activity, and we are looking at activity start time attribute of that. What would you expect the distribution to look like? So what I have out here is a timeline, midnight to midnight, and the probability. So what do you think would the distribution of the start time of eating activity for a typical human look like? Anyway, thoughts?
Maybe there would be a peak at 8 a.m. for breakfast,
Okay, so
12 p.m. for lunch.
so you'll basically have some peak out here, some peak for lunch. Yeah. And some peak for dinner. And of course, the other thing is a lot of people skip breakfast, perhaps more have lunch, everyone have dinner. So maybe the heights might be different. Okay, so something like this. I don't know. Okay, depends on country and culture and time of year and stuff like that. But we'll kind of expect 3 peaks. Okay, given these, and then I guess there are night owls and also might be there some kind of midnight peak also. Okay, but anyway, so you're right? So it's no longer just Gaussian, right? That's the main point. It just doesn't look like a single Gaussian. It probably will have some sort of thing. I guess these guys are assuming more people have breakfast and some skip lunch and something, Okay, anyway, whatever it is, it's a summation. It's a mixture of these Gaussians. So that leads to kind of the common generalization in case of continuous, which is called Gaussian mixture models, and it's basically saying that any given attribute, we are going to think of it as a summation of some number of Gaussians, and we pick that. We pick m Gaussians. So we basically say that probability of xi given y equal to k is a summation of m Gaussians, Gaussian distribution, and so each one of the Gaussian distribution has a mean and a sigma, and then we are also going to weight them. So it's a weighted mixture of those. Okay. So we basically, in this case, we have parameters here, here, and here. So we have a total of m times 3 m parameters for each case. Okay. Additional constraints, weights, the phi m have to be greater than or equal to 0, and the summation has to be 1. So it's the standard weighted kind of thing that you put. And you could generalize this thing if I had multiple attributes, then we basically say that each Gaussian here is actually over all the attributes. So it's a multivariate Gaussian. So their mean and sigma will have dimensionality d, where you have d attributes. So they become dimensional vectors. So now the task basically becomes how, given the training set, you have to estimate these parameters. So if it is vectors, then it becomes 2md plus 2md plus n. So it's 2m plus 1 times, 2d plus 1 times m. Okay, that many parameters. So more generally, 2d plus 1 times m parameters, where d is the dimensionality of the vector. Okay, so and that is for every combination that you would take. So our job basically becomes of one of estimating those parameters, and by this time you are kind of in the world of applying kind of numerical algorithms and stuff like that. So the one which is used here is called expectation maximization, and I'll not go through the details of the algorithm, partly because you don't ever need to, because this phase training you are going to use one of the tools, but just it's nevertheless interesting how conceptually these things work. So you start with an initial estimate. So you give some initial value to all those parameters. Okay, and very commonly done is you will say mean is 0 and standard deviation is 1 or something like that. Some kind of reasonable looking initial value, and then basically the whole algorithm operates in two phases, an infinite loop, whatever, a loop over two phases, expectation, maximization. So the way it works is the expectation phase, what happens is there's an E step, each data point we will assign it to the nearest mixture component. So remember, based upon our initial choice, so when we start out, I have a bunch of these Gaussian peaks, and I'm going to take a data point and I'm going to assign it to one of the peaks. The peak I'm going to assign it to is the one which is closest, okay? And once I have done that, then based upon that assignment, I'm going to calculate the new peaks, okay? And I keep repeating this process until there is some convergence that is happening. So this kind of algorithm is very commonly used in cluster assignments and all. It's basically that's all that is happening. So it's super simple, conceptually at least. But again, this is the part where tools like scikit and all do their job very well. So you don't need to worry about these yourself. But it's good to understand. Again, probably you may have seen it in some course, some of you. Okay, so the next thing I wanted to do was talk a little bit about some uh, other models which are there. So what we have now seen are kind of two models, knife Bayes and Gaussian mixture, which kind of handle window at a time. But we also talked earlier about this kind of view that we can think of the underlying world, the person or space or whatever, kind of moving from state to state to state. And so instead of looking at what state you are in, just based upon in the current window, based upon the current observations, more generally, you would need to somehow factor in what happened in the past. It's not an independent decision in terms of time. Somehow you have to factor in what happened previously. So this leads to uh, uh, models which are sequential in nature, where the idea is that you make a decision by also incorporating some knowledge about the past, which is kind of like a state. So your decision is based both on the observations you are currently making and the state that you are, the history. So, okay, the history that you are in. So typically these things imagine the world that underlying there is a state y, which we label as y. So at time t, the state is y of t, and it's again some multidimensional state. The state here refers to, I guess I'm using the word state in two very different settings. So just to clarify, the state here means the activity we are engaged in. Okay, so y of t may, for example, say it is washing or running or driving or stuff like that. That's what I'm kind of referring to out here. So underlying process is in some activity state, which takes, this is the label that I'm interested in really, right? That's what I want to know. But I'm making an observation, which is the sensor observation, or rather the features of the raw sensor measurements. So these are already features, okay? Um, so that's what I'm observing. And what's happening to the system is that it's moving from state to state to state. So from one activity to another activity to another activity. And as a result of that, it is emitting these observations. It's possible that I may stay in the same state. So it's possible that I was sleeping in yt minus 1 and I'm again sleeping in y of t. That's certainly fine. So I have a finite set of labels, and y of t or whatever y of I takes values from that set of labels. So for example, it's possible that y of t may take bunch of these possible values: prepare meal, medical dispenser, watch DVD, and write birthday card. So there are these 4 different underlying activities that we are able to take. And I have a bunch of sensors. M17 is motion sensor, D07 is some door sensor, I06, I03, I forgot what they stand for, motion sensor, inertial. So inertial 06, inertial 03, inertial 08. So what you see out here are a bunch of sensors, and we are getting events from those.
So X are the features pertaining to the activity Y.
From the sensor. So when the system is in this activity, the sensors made some reading, and I computed the features over it, and that's what I'm calling X.
So this is more of a you cannot directly call it time series, but time-based approach.
It gets time series, right? So I will get a feature vector here, I'll get a different feature vector time t, another feature vector time t plus 1. So I'm getting a sequence of feature vectors. It's a vector time series, okay? And my goal is, given this sequence, I want to figure out what value did by t minus 1 have, what value did by t have, what value did by t plus 1 have, and so on and so forth. Is this clear to everyone? So again, I'm getting a observation which is a time series of vectors, and based upon those observations, I want to figure out the underlying time series of labels that was there. Now, these labels are not independent, so we capture that fact. So see how there are arrows going between some of these labels. So what this is saying is, if I if the medicine dispenser activity took place, that is of medicine, then after that I can go to prepare meal or watch DVD, but I cannot go to write birthday card. So this is equivalent to saying that some words can follow other words, but not others, right? Or more generally, it would be something probabilistic, right? So if I am lying on a bed, then the probability that I will drive a car as the next state, given assuming my time windows are short enough, is basically zero. Okay, so that error will not exist. But lying on bed, maybe it's possible that I may go to shower or go to pick up the newspaper or whatever various alternatives that can happen as a next step. So there will be multiple arrows going out. So so what you see out here, these arrows, this thing is kind of defining my activity model. Which activity can follow which activity? And generally speaking, there will be some probabilities out here. So like from medicine dispenser, maybe more likely I will go to prepare a meal than to watch a DVD. Most things like that possible. Okay, so there would be some sort of an underlying grammar of life, if you may, which places constraints on our activities. Not every activity, from one activity to another activity, is not equally likely. Okay, there is some shape and form that there's some constraints that exist. It may vary from person to person. It may vary time of the year. It may depend upon day of the week, stuff like that. But at the end of the day, there is some underlying model that sort of exists. Okay. And then while you are doing one of these activities, the sensors that may report events, the other arrows are indicating those. So this is saying that if I am in the prepare meal, then M17, D07, and I06 are the ones which can report events. The others are not, possibly because perhaps maybe inertial 03 and inertial 08 may be belonging to other members of the family who don't cook, and motion sensor 14 may be in an area which is away from the kitchen, for example. Okay, so which sensors are possible? So you see again that some of the sensors like I06 can happen medicine dispenser, and prepare meal and watch DVDs. I08 on the other hand can only happen with watch DVD and write birthday card, but never happens with medical dispenser because presumably this person never takes medicine. So so there would be some some constraints like something like these would exist in the data, and that's what you are going to learn. You are going to learn that I08 it has some probability given like birthday card, it has some probability given watch DVD, but this probabilities with others are zero. So there are two things going on out here. There's a model which, by virtue of its structure which activities can follow or see. Um, okay, that constrains things because if you start out by saying any activity can follow any activity, then you are not making use of any prior knowledge. So one way we bring to bear prior knowledge out here is to prune out edges. We can just say some things we know are not possible, and now we are going to learn the rest. Because otherwise, I will have everything connected to everything. All activities can lead to all other activities, and all sensors can be triggered by every activity, and that would be too many parameters. So we prune based upon prune edges based on prior knowledge. This is simply to reduce the number of parameters because each edge corresponds to some sort of a probability, and the more the parameters, more horrendous is your parameter estimation task. Then, to make the whole problem tractable, we make two additional assumptions. One is, which comes from the name, Markovian. So this is the first one. It basically says probability yt plus 1 given the history of the states I was in, activity states, is the same as probability of yt plus 1 given y of t. So only the activity state in the preceding time step matters and nothing before that. So that's the Markovian assumption. And the second assumption, and there's also another, these things are all finite valued because otherwise you can always cheat and say y of t is the entire history of activity, the vector of or the entire state in which is ever growing. Okay, so it is finite bounded states. Okay, and then the second assumption we make is that the sensor observation at current moment of time, given the current state and all the prior states, is the same as sensor observation given the current state. So again, sensor observation depends only on the current state. That again is a reasonable assumption unless sensors have lots of memory, okay, which I think in most cases we can ignore. So these are two crucial assumptions. Given that, and given a graph like this, we can then, using this famous Viterbi algorithm, which by the way has an interesting history. Viterbi algorithm was done here at UCLA, although USC advertises it differently because Viterbi was their professor. Viterbi was their PhD, but he was a faculty in the precursor of what are now ECE and CS departments, and this thing was, I guess, done here. It's basically what is a dynamic programming algorithm, but done in context of communication and signal processing. Using that, you can compute two things. You can say probability that a particular activity model produce the entire sequence of the sensor observation. That is, you can, so if I give you a sensor observation, a sequence of X vectors, I can answer the question, what is the probability that a model whose parameters are all given, what's the probability it would have produced it? Okay, so you can say, if it is very low, you can say it's very unlikely, right? And the second thing is, we can also say which state sequence could have produced it. Remember, a sensor could be triggered by multiple activity states. So you could also say this observation happened because the person took medicine and then watched DVD, for example. Okay, so we can provide an answer to that also. Details, again, too advanced for our purposes out here, but given the model, we can answer these kind of questions, and that's it. What are the parameters out here? So if you think about it, parameters are really the probabilities that are associated with that model. So they really include three things. Probability of y1, that is, what did I start out in? Okay. Probability of yt given yt minus 1. Remember, we already made the Markovian assumption. So probability y of current state being, let's say, medicine dispenser given that the prior state was prepare meal. Okay, so this is a parameter which we need to learn. And then finally, probability of xt given by t, which again, because of our assumption, that's all that matters. So that's the only other probability which is left over. And then finally, you could do a further simplification. You can say probability of y1 is nothing but probability of y1 given y0. And y0 is kind of some sort of an activity state, which is kind of like a root point, a start point. And then the goal of the parameter learning is the following, that I have training data, and in that training data, there exists labels y and the corresponding measurements x. So I have a whole bunch of xy. And what I want to do is I want to find those values of the parameters which will give the observed distribution a high value, a high probability, right? So given, again, the goal is find those values for these parameters such that the observation x comma y has a high probability, or you want to maximize that, right? So that's what we are seeking to do in solving this. How you do it is through some sort of a underlying parameter estimation algorithm, which again kind of works like those expectation maximization, those kind of, these are iterative algorithms. But basically, you start with some sort of an assignment and you kind of perturb it until you find that probability x comma y is maximized. Again, tools do it for you. Sadly, scikit, which is what we use, does not have HMM in it. It used to, then they deleted it. I think there are other tools which provide it, but unfortunately, that doesn't exist in scikit. But this is kind of like a natural fit for a lot of sensory applications, if you think about it, because there is this sequence nature, activities to activities. It captures very well constraints that exist in our life. So it helps smooth wildly weird labels. If you are simply doing window at a time, you might face predictions which clearly don't make sense because you're not making use of the previous thing. So the system is unable to say that, previous window I predicted sleeping. It just, and now I have two possibilities. The person was whatever, doing treadmill at home and jogging, which is more likely. Okay, I mean, you might want to kind of take into account the prior prediction. Okay, so essentially, what HMM lets you do is temporal smoothing. And there are other ways you could do it, but they tend to be hackish. Whereas this is doing it by taking into account kind of a very systematic model that exists under the hood. So while scikit doesn't have it, there are lots of other tools too. This is pretty widely used. This is until the year 2010 or so. This was pretty much what was used in speech recognition also. HMMs were used there. After that, it's deep neural networks. But for 25 years prior to that, this basically ruled that space. So pretty powerful tool, simple enough to do on embedded processors. The sad part though, like I said, is it's not as well supported on kind of some of the more prominent tools that exist. Any questions on this? Okay, so next one, which I'm going to just flip over because scikit provides support for it, and I'm going to walk through a scikit exercise to show how to use that. Not with decision tree, but just again a built-in classifier there. So decision trees basically take the norm that on the feature values, I'm going to go through a sequence of decision making, as the thing implies. So might first say, let's see what value does attribute count bathroom sensor have, and depending upon that, I will then follow. So if this, do this, and then kind of the sequence of decision making. And this is something which kind of mimics the way, I guess, we humans often do decision, right? I mean, we kind of, based upon some course variables, we kind of go through a sequence of decision making. We often call this thing logical reasoning, right? So that's what's happening. And in this case, your goal is to both learn the structure as well as learn these threshold values. So usually these kind of systems restrict the type of decision trees you may have. Like for example, they may limit themselves to binary decisions. They may limit to the kind of predicates you are allowed to use out here. Like in this case, you see it's only one predicate at a time. There is no like a Boolean expression sitting out there. So there are constraints that can be placed, but this is a very common model which is used, and there are they do pretty well. They do extremely well, and there are variants of it where instead of just using one tree, you may have an ensemble of trees called random forest. So you basically have multiple trees making a prediction, and then you kind of fuse their results into one. So as you can imagine, it is easy to implement, given there is just this is just embedded in the logic of your program. So decision trees very commonly used, and the final one is kind of a generalization of linear classifiers. So the idea behind linear classifiers is that given the vector x, assuming it's all numeric, I'm going to multiply it by some sort of a weight matrix and then add some sort of a bias. And then I'm going to test whether this is less than greater than some threshold. That's a simple linear classifier, so some sort of a decision boundary and kind of a weighted sum with a bias. Um, so support vector machines kind of generalize that concept. So it basically says, let's imagine I'm looking at my n-dimensional feature space, in this case two-dimensional. I have points, uh, I have training points, so I kind of see the black points being hand washing, sorry, sweeping, and the white points being hand washing. And what my goal is, try to find a decision boundary between these. So in this case, it is just going to be a line, but in a general case, it's going to be a hyperplane embedded in a n-dimensional space. So if we see in this case, the points are clearly linearly separable. That is, I am able to find there exists a line so that all white points are on one side, all black points are on the other side. And in this case, the question becomes, what is the best line? And the idea is that the best line is the one which maximizes the distance to the closest point. So okay, so essentially what this is saying is that the black line is good because the nearest points are kind of far away, and whereas like one of these dashed lines, while acceptable as a classifier, but the black points are too close to this lower dotted line, and likewise the white points are too close to the other dotted line. So there is kind of like a no man's land around the black line which you want to maximize. So for example, I could have this alternative. Let's say this line, that would be a bad one, even though it is linearly classified.
Is this taking into account the Euclidean distance, or
Yeah, the distance could be any distance metric, but Euclidean is common. So what distance metric you use kind of depends, but again, Euclidean is pretty common. Yeah. Huh?
is it the most usual one, or do people have different?
Almost always you'll use Euclidean. Okay, but all these systems allow for various distance measures. Okay, But so you can have Manhattan distance, so various norms, L1, L2, L3, L4, whatever you can. But again, L2 norm is the most common one. But whatever distance measure you pick, the goal out here is that I want to maximize the distance to the nearest point. And now, more generally, I'm going to have not just a binary classification, I'm going to have multiple M classes. So the way kind of you can treat that M class problem is as multiple binary problems. So let's say I want to say three activities: hand washing, sweeping, and sleeping. Okay, so first I can do a binary classification of hand washing versus the rest. Then I can do sweeping versus the rest, and then I can do sleeping versus the rest, and then I pick the one which is most make a choice across those. So I can approach it as in that manner. Okay, so this case was easy. I need to find a hyperplane which maximizes this. So the closest vector, the points which are closest to the chosen line are called the support vectors. That's why the name support vector machine. That is, these are the points which are kind of uh, are constraining my line basically. Now, the harder problem which occurs is when it is non-separable, which is often what the real world data would be. So in this case, again, I have black and white points, except there is no straight line which uh, which provides that separation. I can do some sort of a curve, a curved surface or curved line in this particular case, but you don't want a high dimensionality line, high dimensionality curve because it loses, it becomes too specialized to this. So I could create, if you were to not limit me to line, I could create something like this, right, as my decision boundary, except you perhaps don't want to. And this is where kind of a balance has to come in. Clearly, linear is not always sufficient, and yet you don't want to make these decision boundaries which are squeaking, which are catering too much to uh, outlying point. So in this case, we're sticking to straight lines, but generally speaking, you want your decision boundary to be kind of well behaved, low dimensionality. So straight line. So how do we define in case of SVA? So the idea now is that points are penalized uh, if they are on the wrong side of the boundary. So this white point, because it is lying on the wrong side of the boundary, is going to contribute to my cost function, and I am going to therefore penalize it. But we give a little bit of a slack. We say that the points which are within the margin area, they don't get penalized, but they begin to get penalized after that. Okay, so you basically penalize. External distance. This way of defining a loss function, uh, that is how to penalize, is very commonly used in neural networks and all sorts of things. That is, you penalize based upon the distance from how wrong uh, the decision boundary is. So that's the second challenge that you face. Now, what may turn out is that maybe I give you a point cluster. So I have two classes, and it looks something like this in my feature vector space. Now, in this case, A straight line obviously doesn't exist, but as you can see, there does exist a pretty low dimensionality curve called a circle. Okay, so I could use that. So my decision boundary could be a nice low dimensional curve, a circle, and I want to be able to do it. So what could I do out here? So one is I could say, look, I'm going to now suddenly start dealing with things other than hyperplanes, all sort of other shapes and all. But the alternative is that I transform map x to phi of x, where phi is some nonlinear function. So the idea would be I'm going to take my points and warp them into a different geometry and then apply linear classification there or SVMs out there. So, so usually something low dimensional. What's a circle? Circle is basically in sort of a quadratic x square, y square. So if I think in terms of those, I can warp it into a linearly separable thing. So what is usually done is that you'll take your x vector and then you are going to consider some nonlinear kernels, as they are called, which warp them into a nonlinear space and then apply the SVM. So that leads to support vector machines for nonlinear kernels. So linear kernels basically just operate on the feature vectors as they are. You have low dimensionality polynomial kernels. You have radial stuff, hyperbolic. There are a bunch of choices that these systems provide. But the intuition is that while in the original space, feature space, linear separability may not be possible, but by warping them into nonlinear space, I could do a linear separation out there. Okay, and again, the choice of the kernel is something that you could either play with because you have no idea what things look like, or alternatively, maybe you have some physical intuition going in, and therefore you're going to, try these things out as well. Okay, any questions? Okay, so let's do the following. Let's take a 5-minute break, and then I want to switch gears. I want to kind of walk through how to run through a scikit example. We'll do a. I'm not going to be able to run the whole thing because the SVM learning takes an hour, but I did it at home. So, but I'll show you how the steps are. So let's do a 5-minute break, and then we continue.
The screen, right?
Yeah.
So on the last one, you showed us all the different kernels and whatnot. Are we supposed to know how to apply those or like create new kernels?
No. But I wanted to bring it out that if you are using SVM in your projects, when you are reading the manual entry for these things, you should know why they exist and why should you apply them. Okay. Yeah.
So in the hidden Markov model, we assume that our state is Markov, so it only depends on the previous state.
Correct.
But
So
then when we make the inference, we assume that we want to maximize the probability.
We want to maximize that the sequence is what is the most likely pathway through the y1, y2, y3, y4 explains this observation.
And that's still Markov. Yeah.
No, there's nothing Markov at that stage. Now I'm given what is called as a Bayesian network basically, and I'm trying to find what transition through that Bayesian network that explains this thing. The Markovian assumption came in right when we said y of 3 is only a function of probability y3 given y2, y1 is equal to probability of y3, y2, because I eliminated a whole bunch of parameters then.
Yeah.
Okay, so that assumption got embedded in the structure of the graph now, the set of parameters I'm dealing with.
Yeah.
Okay.
感觉好像是不动滑。然后跟你觉得
For me, about it, I was doing it for 2 days continuously, and nothing happened till last night, 2 a.m. When I got it to work, it happened. I wanted to show you guys the demo of what I did. So I probably just threshold makes it look like doing what you guys should do. Because I have that over
Okay, let's start. So what I wanted to do was to kind of expose you to uh, some of the tools that exist to be able to do the training. And of course, if you want to just do backend inferencing, you could actually even run these things on the Raspberry Pi if you wish. So if your approach is, I'll compute the features and push it out, or just push out the raw sensor data and do all computation on Raspberry Pi, this is also a possible approach to take. Okay, so there are obviously many tools that exist in this space, and cloud services like bigml.com that actually is a very nice yeah, so I've often used this thing a lot, which is basically like a cloud service. You can access them through API, you can push the data and get the results back, you can deploy models there and all, except for free accounts, they basically give you only a modest amount of thing. You could also create these kind of things on Google, Amazon, there are a bunch of things. But I'm going to basically focus on what you can do on your own computer. So scikit-learn is basically a machine learning package built on top of a whole bunch of other things in Python. And as you can see, it provides support for a bunch of these key capabilities: classification, regression, clustering. We talked about all of those. Clustering is unsupervised, regression is numeric prediction, classification is a label. Dimensionality reduction, so you just want to reduce uh, I guess, the form of a compression, if you may. Model selection, and then pre-processing support for all of these things. And if you go under, since we are mostly interested in the classification in this work, so you would see they have all sort of things. So like they have linear models, they have support vector machines, they have optimization approaches. That is, how do you find the parameters? Gaussian processes, we kind of saw those, knife-based, decision trees, and so on and so forth. Okay, so they have a whole bunch of stuff already out there. Uh, so we'll see how to kind of use these. The other thing is, where do you get the data from? So our sister campus, UC Irvine, they have a UCI machine learning repository. So lots of very interesting data. So if you just want to play with things, that's where you get. The particular one which actually I'm going to use is called human activity recognition using smartphones. So this is basically some research group some years ago collected from 30 human subjects data from the sensors in the phone and doing a bunch of different kind of activities that I'm going to describe shortly. And then they have actually pre-processed it into features. So what you download is actually not the raw sensor data, but actually the feature vectors corresponding to those. So that exists. Final thing is, and which is extremely useful, is Kaggle. Any of you heard Kaggle before? Some of you, okay. So Kaggle is where competitions for machine learning and all are done. It's a beautiful way of on your own kind of getting engaged in this field. So they basically do all sort of competitions, some of them sponsored by companies like Google and all. In particular, using this particular data set, they ran a competition and were somewhat old, as you can see, a couple of years. But what has happened out here is, firstly, there is data, obviously. So they have put the data in a nice form, test.csv and train.csv. Pretty much the norm with most of these tools is to use CSV as the exchange format. So your goal should be to get your sensor data or into a CSV form, and then you can within the very good tools to kind of work with within the Python world. And then the other thing is that people who have attempted this competition have created their own solutions, and they have posted these things. Okay, so you would kind of see like each one of them basically publishes a Jupyter notebook. How many of you have used IPython notebooks? Again, some of you. Okay, so if you're using Python, then the thing to use is Jupyter Notebook, okay, or called IPython Notebook. It's basically what happens here is that a program runs in the backend, and it basically exposes and it talks to the Python program, and it exposes itself through a browser-based interface, and we'll see how it kind of works. But the nice thing is your Python stuff may be running on some remote server, and you can just access it using the browser anywhere. Of course, you can run it locally, as I would be doing it. Super easy to install, and great way of basically writing your kind of it's a living document basically. Okay, so we'll see how sort of it works out quite nicely. So in this case, what Kaggle does is it also provides the ability to run these notebooks, and also you can fork a notebook and then modify it and run it if you so wished. But I made a local copy because I was kind of modifying it. Okay, so there are a whole bunch of solutions out here. What I based mine on was this guy, recognizing human activity with 96% accuracy, as well as something I found on GitHub. Okay, finally, I am running the Jupyter Notebook. So essentially, if you're working with Python, what I find very useful is that every time I work on a different project, there are different combination of packages and all that I need. So Python has something called virtual environment, which basically give you within a folder, a contained kind of thing where for that application you have a set of packages installed, and then you can do it differently for a different thing. So there are many ways of going around it. If you are on Linux or Mac, there is something called PyEnv. simple Python version management system, I find this the best to use. But you could also download one of the self-contained distributions, which if you're on Windows, probably that's what you have to do. Anaconda is a very good release. I don't like it because it has sufficient variations from standard Python. So I like PyEnv, and I think I would recommend using that if you are on Linux or Mac. But if and also if you are on Windows, Windows 10 newer than the some sort of a centenary edition, some anniversary edition. Yeah, if you have anniversary edition or newer, then it has a Linux subsystem, and therefore you can essentially run the way you do under Linux. If you have anything precursor to that, then lot of, even though Windows 10 had Linux subsystem, but a lot of things didn't work. Anyway, I don't use Windows, so uh, I guess some of you had upgrade problems after that, but you sorted it out.
It supports Mac also.
Huh?
Anaconda does.
Anaconda is on all platforms. I don't like Anaconda simply because its package installation stuff and all is different enough. PyEnv gives me the clean native Python. So for example, if you are on TensorFlow and you want to use GPU, then you can't do it through the Anaconda thing. Okay, so there are these kind of constraints. So I think it's better, generally speaking, to stick with baseline tools, and PyEnv basically gives you virtual environments and everything, so it works nice. Okay, so uh, so now let's walk through a particular example out here. So unfortunately, let's see if okay, this should work. Okay, so uh, so what you're seeing out here is actually before that. So when you fire up Jupyter Notebook, you kind of get a screen like this, and you can create a new thing. So you can create various kind of files. You can create a new Python file, and now you have a Python thing running in the browser. And to evaluate, so you write text in a cell, and to evaluate it, you press Shift and Return, and it calculates it. Okay, so okay, and so that's the basic okay, so back out here, there is some usual importing thing and all. Some useful things, just I find quite, there's a Python debugger, and which lets you breakpoint and all, which is very useful. And then matplotlib, which lets you plot inline plots, very useful. So first thing we do is we download and read the higher data, the human activity recognition data. So basically what happens in this data set is that the users were doing one of the 6 activities: walking, walking upstairs, walking downstairs, sitting, standing, and laying. Okay, and while they had the phone tied to their waist, tied to their hips. And it's a old data set, so pretty old phone. And oh, before that you have to download the data from Kaggle. Unfortunately, they require you to sign up before you can download the data, so you have to do that. So it gives you the test.csv and train.csv, and I put it into a subfolder called data, and then I use pandas. So what pandas is a package which represents data as a data frame. Data frame is a table of data with columns representing attributes and rows representing samples of data. It's like a Excel spreadsheet or a CSV file, but it was popularized by the language R and S in statistics, and is very commonly adopted out here. And what it lets you do is all sort of fancy querying operation. You can say, I'm interested in all those rows where the value of attribute age is greater than 50 and stuff like that. So you can do all sort of fancy querying. So it becomes kind of a useful tool to have. So I load it into these 2 variables. And then if we look at the data, So each column represents an attribute, and there are like 500 plus attributes. Okay, the other thing you would see is that they clearly have missing data like -1 and stuff like that. So the kind of problems that I was talking to you about is present in all these data sets. Okay, anyway, so it's a gigantic CSV file with a whole bunch of things. So what we do is we basically look at how many features and how many records, how many columns and how many rows exist in a training data set, in the test data set. We look at what we do is we draw. So one of the challenges you face when you are dealing with sensory data is the following: you will have multiple subjects, different humans, and them doing multiple activities. And the question that becomes that how do you go around, what kind of model are you interested in? So one version is you are interested in a personal model whose purpose of that model is to predict money's activities. And therefore, I'm going to train it on my data and it's going to make predictions about my future. And it will never be applied to anyone else. Now, of course, the challenge with this is that I have to go through a lot of training. So another alternative would be that we start out with a general model, a generic model, and then we additionally fine tune it with my data. So we do some additional work and fine tune it. Uh, in that general model case, what you also want is the ability to generalize to different users. So if, let's say, Apple is putting a classifier for activity in iPhone, they obviously have to make sure that the people they are training that model on is not a biased set. Let's say if they only do it for males or only do it for short people, then there will be generalization problems. Sometimes you may have a few different clusters of models. So you may say for female and male, we'll have two different models, and you ask the user the gender, and then based upon that, select the model. So there could be subject dependent or whatever, person dependent and person independent models. Um, the other thing is you want to also make sure that how are you testing these things. So the best way to test would be if I have 30 individuals, I'm going to set aside some individuals and not include them in my training set at all. What I'm showing you out here is not doing that, but I think better would be to set aside some users which were not there in the training set so that you can truly test for uh, in, uh, independence. Okay, so one of the things we do is we drop the subject because we don't want to use the subject as a feature because it appeared as a column out there, because if subject gets used as a feature, then it will basically become very person specific and you don't want that. And then we also drop the activity because that's really the ground truth, that's the label. So you obviously don't want to have that as a feature also. And the label consists of the activity. Okay? And we do that both for the training data and the test data. Test data, we're going to set it aside. After we have trained our model, then we are going to evaluate it. You should not be looking at the test data. Okay? But during training, it is also important that you create a model which has good generalizability. So what we usually do is that is called cross-validation. You take your training set and you split it into two parts, usually 80-20. You train on the 80 and you monitor the performance on the remaining 20, and you keep shuffling this thing. So you do 80-20 and try a different 80-20 balance and do it multiple times, and kind of this way you get a more general model. So on this cell, all we are doing is we are basically just labeling things out, putting things out. So what you would see is, for example, the training data eventually has 561 columns. So we started with 563, but we dropped to activity and subject ID. And my training data has 7,352 measurements, and my test data has 2,947 measurements. So if I were to be running it, I would again do shift return and it just calculates pretty quickly. Now, the first problem you may face is that your labels may not be in the right form. So usually labels are things like strings or some numbers and all, but almost all packages and algorithms like to see labels in one of two forms. Either they expect output is, if I have C classes, output is 0 to C minus 1, or they expect that output is a one-hot coded vector of shape C, comma. So what I mean by that is that output is a vector with C positions in it, and the value would be 1, uh, corresponding to the label that is being predicted or is a correct label. Okay. Both are encountered, and within the same tool set, some sklearn things use one, some use other. So you have to be very careful, because this can be a source of a little bit of a pain if you don't realize that, oh, the function you're using is expecting the first model or the second model. Okay. In case of binary, the two become equivalent because just one bit. But fortunately, so even though our labels were these strings, fortunately in scikit, as part of their preprocessing package, they provide a label encoder. What the label encoder does is it takes, looks at the set of labels, and then finds the unique set and encodes them appropriately. So what you see out here is that I create two label encoder objects, ltrain and ltest, and then I feed them the training label and the test label data sets. And then I get the train label and the test label out of that. And you would see what the labels are in this particular manner. So first thing, encoding, so that my labels are now in that particular form. Then we seek to learn a support vector machine. So we already talked about the support vector machine, which is maximizing the distance to the closest point. So we want to find this hyperplane which has that characteristic, except that in our case, it's a hyperplane with 561 dimensions, or whatever. Our space is 561 dimension. It's a hyperplane in that space. That's way too many features. It's going to even if you learn a model over it, you have to carry around 561 features, and you'll have to wonder, are all those 561 features useful? Maybe a lot of them are correlated and all. So you need to prune them. You don't want to just carry along all those features with you. So what features to use becomes an important aspect. And fortunately, scikit provides lots of feature selection possibilities. Okay, so they have a whole bunch of library functions there. The one we are going to use is called recursive feature elimination. Basically what it does is it kind of searches through the set of features to identify which subset gives a good set. So intuitively what you would expect is, if I use very few features, the performance will be bad. As I start increasing, at some point it will saturate, and then not much gain is coming because the new other features are not giving me any new information at all. So you would expect kind of some sort of a rising curve and then flattening out. So what you want to do is you want to get the knee of that curve, where the big gains are going to be, up to which it is beneficial. So we again import some additional stuff, but the main thing out here is we are using SVM, a particular type of SVM called SVC, C support. We are using a linear kernel. We use that recursive feature estimator. What it does is we pass to it the SVC, the model we are seeking to use. And we also specify some other stuff here. What is a criterion? Like I'm interested in accuracy, for example. And then what it does is it does recursive calling and optimization of this thing. So it's trying to find the model parameters and simultaneously doing the feature pruning. And it kind of goes into a loop which takes a long time. If I didn't want to do it, if I simply said, let's try these 10 features and learn an SVM model, that would be pretty quick. Here what's happening is kind of this intense loop and all, so that's why I have this thing. It takes, on my laptop, it took close to an hour and a half to do all this stuff. Now here, all I'm doing is I'm creating the objects. So all of these things are just for not running anything. This is just creating the object. The other thing is I also want to shuffle the data set. So I do that. I shuffle the data set to get shuffled testing shuffled data. And you could see that the first 5 entries in my data set originally were all twos, but now they're kind of a medley of things. So very important to shuffle things. And now we run it. So we run refcb.fit and pass in the training data and pass in the training level. And then we are all going to both plot the number of features versus processing time, as well as number of features versus how the accuracy changed, and we are also printing the accuracy time. So optimal number of features 373. It took hour and 20 minutes, and then the score that we get. So what you see is something like this: that as I increase the number of features, the score, which was the accuracy in this case, initially rose and then pretty soon plateaued. And so the sweet spot is going to be somewhere around out here, and you're going to play with this thing. Now it found that the optimal number of features is 373. Question?
I was just wondering why it's convenient to shuffle the data.
Why do you need to shuffle the data? Because what may happen is that if you repeatedly see data from the same class, then your model is going to go one way. And then, so it gets too biased. So what you want to do is at all times, you want to show it a representative set of data. So it's kind of like intuitively, if initially I come to this country and I only encounter tall people, then I'll say, hey, America is only tall people, okay? And then it will take me a long time to dig myself out of that hole. So you want to expose the model to a balanced set of data so that it's learning properly, okay? It's important for the training phase. For the testing phase, it doesn't really matter because you don't average out over the whole test. For some reason, place where I copied was also doing the shuffling and testing, but it's not needed there.
For like a given set of training data, like the order in which the data is implemented.
Yeah, so basically, usually the data is coming from a source which likely is not sufficiently random because, for example, maybe you collected all the jumping data first and then you collected all the sleeping data. So your initial file may have these biases. So you just randomize them. Okay.
So that's true, especially if we do cross-validation, right?
That
We
is
want
true,
to-
especially if you do cross-validation. Now, one thing you have to be careful out here is that if you are doing this is when we are making independent things on every row. If I'm doing the HMM type stuff, then the sequence does matter because then we are saying that things are going in a time sequence. So their shuffling doesn't make sense in that case. But what you can shuffle there perhaps is different days. So like don't just have all the weekends first followed by, okay, you kind of, whatever is your segmentation that you are doing, like whatever is your notion of a time series, okay, within a time series you cannot shuffle, but you can shuffle different instances of time series. So shuffling is basically taking care of any biases that may otherwise creep in. Okay. So this thing, the big win out here is that we went down from 561 to 373, so kind of a 40% or so gain, which is good to have. Just makes the model more efficient. There is some other work on this data set which goes down to like 150, 200 features with obviously somewhat lower accuracy. So you want to kind of work with those. What this also shows is that across the different features, how well they ranked in terms of their like which. So one means very important and kind of so and so forth. So this is basically just rank ordering. There's a whole bunch of features which are ranked bundled at the top together. Okay, and then the other one. So these are just different ways of looking under the hood what is happening. Another thing that it does is it looks at the feature correlation. So among the selected features, it just does correlation things. So it kind of, so naturally along the diagonal you would expect good autocorrelation, but then other places it is kind of more diffuse. What ideally, I guess what you're looking for is features that add value, okay? Because features that are duplicative, they are kind of pointless to have basically. So that's the basic thing. I'm going to post a link to this thing on Piazza. You can play with it yourself. But other things that on top of this, firstly, play with different kernels. Now, 96 plus percentage accuracy that we got on this one. Here, let's see. Yeah, here, 0.9647. So 96.5% is pretty good. And this is on the test set. So it's a pretty good accuracy. I think though, I must caution you. I think one of the flaws that I think there is in the system is, in the way they did it, is that the test included participants on whom training was done also. So I think a better way of test would be to set aside some participants and test on those. So that is what I would strongly suggest in a sort of a good quality system, because only then you are getting the true generalizability. Currently, this testing is looking at is getting a peek at the test data also. So how you select the test data is not simply they selected some records and set them aside, which these guys are doing, but how you select those records is also very important. So a better system out here is going to take subject ID into account, and based upon subject ID, create a test set and separate them out and never incorporate them into training. Okay. So I'll try to modify this thing at some point. So that's better selection of this thing. Different kernels, different feature extraction methods. So we used RFE, but there are a couple of others there, so may lead to different results. And different algorithms for the machine learning itself. It's just SVM. So nice thing is that in this basic framework, if you want to try something else among the available set of models, all you need to change is this line. Okay, different kernels, different algorithms. You want to try a decision tree? That's all you change. So it's pretty easy and simple to kind of work with, and good. So this is kind of the basic template to how to go around doing it. Now, what we don't have in this picture is, okay, now I have a model. Now what? So you can examine the weights of the models and all, and then have to figure out a way of encoding it. This is where simpler models like simple linear models and all have an advantage, which is there are fewer parameters to deal with, so writing the code is easy, naive Bayes, these kind of things. So I will do some investigation and see if I can find some good pathway for that also. But right now, basically, your only choice is once you have the trained model, you examine its parameters and then implement them in your code, okay? Which is kind of painful. So the other alternative that you can have, if your system permits, is that you stream the features to your Raspberry Pi and run scikit on the Raspberry Pi and do the inferences there. Okay. So questions? So if you have never played with scikit and these kind of things, it's actually a great thing to do. I'm going to also show you how to use on Thursday on how to use one of the deep learning packages to do similar sensor processing using for human activity recognition using some neural net models. It's just that scikit doesn't have neural network models. I think it might be changing, but at least as of now, it's not commonly there. The two common packages for deep learning are TensorFlow and PyTorch from Google and Facebook. And then there are a couple of others which are more less popular, but Microsoft has it called CNTK and Amazon has called, forget, MixNet. But they are not used for development kind of a work. So in any case, these are great tools to have in your arsenal, even kind of just generally. So familiarizing yourself. Oh, and of course I forgot, there's MATLAB. The problem with MATLAB is the professor license is $1,500 or so, and so I never buy it. But you guys have $99 student license, so you could certainly use that. That's another option, obviously. Okay, so I'm going to stop. We still have 5 minutes, but I'm done with the material. Any questions? Okay. Okay, so see you guys on Thursday.